Hello friends, welcome to DCBA. And we have solved this problem using moment distribution method in our last video. And today we're going to solve the same problem using slope reflection method. And since it's a portal frame and it has got an inclined leg, it is more tedious and more exhaustive in the procedure. So it'll be a lengthy video and a lengthy sum. But this is a typical university type of sum, so it might come in your exam. So let's get started with it. As we know that the first step is always finding the fixed end moments, and by looking at the structure we only have this load which is acting on the beam, and that is why we only have MFBC and MFCB as the fixed end moments. The MFBC is minus 10 into 4 by that is minus WL by 8, and minus because it's anti-clockwise, and anti-clockwise is negative as per my sign convention here, and clockwise would be positive. Okay, so 0 0 minus 5 plus 5 0 0. This is the basic finding fixed term moments. So this is very important, that we always have to take deflections which are perpendicular to the member. That this note is very important, as we see that the structure has got deflected due to this particular load which is acting horizontally, and we have these horizontal deflections delta. Now these are horizontal deflections. These deflections can only be applied to this vertical member. As you can see in this note that the deflections are always, we have to take only those deflections which are perpendicular to the member. So this deflection can only be taken for the vertical member as it's a horizontal deflection. For this horizontal member we require a vertical deflection, and for this inclined member we require a deflection which is perpendicular to this member. So now what we do is that we draw a triangle here, and as you can see that it has basically got two components. Now this is a horizontal component which is our delta, and this is a vertical component, and this is the inclined component which is perpendicular to this inclined leg. Okay, so this is delta V, that is vertical deflection. This is delta I, inclined deflection. We just magnify this particular triangle here, and as you can see this is delta, which is the horizontal deflection that we have, delta V, delta I, and this is theta. This is the angle of inclination, and to find theta it is very easy. It is just tan inverse of 2 by 4, and we get theta is equal to 26.5651 degrees. And then we just need to find the relation between delta V and delta I. So delta V is equal to minus delta into tan theta equal to minus 0.5 delta. So now why this is negative? Because according to our sign convention everything that is anti-clockwise is negative. So basically if you just check, the member BC has this joint C has gone vertical, has got a vertical deflection. Therefore the member BC has been rotated in an anti-clockwise manner. This was the original axis of the member BC, that is before deflection, and after deflection it has become somewhat like this. So there is an anti-clockwise deflection, and that is why delta V gives an anti-clockwise deflection for BC, and therefore it is a negative. Then comes delta I, which is equal to delta by cos theta. It's simple trigonometry here, nothing much. So delta by cos theta equal to 1.118 delta, and this is a clockwise deflection. Now why it is clockwise deflection? Because see, this point C has got an inclined deflection like this, and if you see this is the original axis of my member, and now after displacement my member is displaced in a clockwise manner. From the original axis to the beam we draw an angle, and we need to check that how that angle is going, whether it is going clockwise, or in this case whether it is going anti-clockwise. Okay, so that will basically tell you how your deflection is it negative or is it positive? Anti-clockwise negative, clockwise positive. So we got delta V and delta in terms of delta. Now we have only three unknowns. What are those unknowns? One is theta B. Since theta A is a fixed point, therefore theta A would be 0, and there is also no deflection for this point. Again here theta D is a fixed point, and therefore there is no deflection therefore there is no rotation, that is theta D is 0, and also there is no deflection. So delta D is also 0. But here we have a rotation of theta B, and theta C is also to be found. So theta B, theta C are unknown, and then we have this horizontal deflection which is unknown. So we don't need to find delta B, delta I separately because we have already expressed them in terms of delta. So it's okay that we find delta. We'll automatically find delta B and delta I as well. Okay. So three basic unknowns: theta B, theta C, and delta. Alright, moving to step 2, which is writing the slope reflection equations. So MAB is equal to MFAB plus 2EI by LAB plus into 2 theta A plus theta B minus 3 delta by LAB. Now, as you know, theta A would be 0 because it's a fixed point, and MFAB was also 0. So 0 plus 2 EI by 4. 4 is the length of AB. Then this is 0 theta B minus 3 delta by 4. So this delta is basically horizontal deflection, which we can apply to member AB because it's a vertical member. Okay. So let us simplify this again. We get 2 EI by 4 theta B minus 3 delta by 4. And this I'll name this equation as 1. Now MBA is MFBA plus 2EI by L length of BA into 2 theta B plus theta A minus 3 delta by LBA. Again MFBA is 0, so 0 plus 2EI by 4 into 2 theta B, theta A is 0 minus 3 delta by 4. Simplifying this we get 2EI by 4 into 2 theta B minus 3 delta by 4. I'll name this equation as 2. Okay. Now MBC. MBC is MFBC plus 2EI upon LBC into 2 theta B plus theta C minus 3 delta by LBC. Okay. Now MFBC has got a value. 2 theta B will also remain, theta C will also remain since these are the unknowns. A length of BC is 4. So let us substitute them, and please take a note of delta. Okay, so here it is minus 5. MFBC was minus 5 plus 2E by 4 into 2 theta B plus theta C minus 3 delta V by 4, because since this is a horizontal member and we need to take the deflections which are perpendicular to our members. Okay, so this is horizontal member, so deflection would be a vertical deflection, delta V. And now we just have to substitute the value of delta V here. We get minus 5 plus 2E by 4 into 2 theta B plus theta C plus, since this was negative, right, minus 0.5 delta, so minus came out, so it became plus 3 into 0.5 delta by 4. I name this equation as 3. Now MCB equal to MFCB plus 2E upon LCB plus 2 theta C plus theta B minus 3 delta by LCB. Okay, again delta would be delta V. MFCB is plus 5, so simplifying this we get this whole equation 5 plus 2E by 4 into 2 theta C plus theta B plus 3 into 0.5 delta by 4. I'll name this equation as number 4. MCD, MFCD was 0, right? Theta C will remain, theta D is 0 since it's a fixed point, and delta would be a delta I because CD is an inclined member and the deflection perpendicular to that member would be delta I, and the length is 2 root 5. This 2 root 5 is the length of the member CD. Okay, simplifying this I get 2a upon 2 root 5, 2 theta c minus 3 into 1.118 delta by 2 root 5. Okay, we'll name this equation as number 5. And MDC is also MFDC plus 2a upon length DC into 2 theta d plus theta c minus 3 delta by length DC. Again delta is delta I. Simplifying this I get 2a upon 2 root 5 theta c minus 3 into 1.118 delta by 2 root 5. I'll name this equation as number 6. So we got all these 6 slope deflection equations. Now we have this very important step, joint equilibrium condition. So at joint B, to keep that this joint B in under equilibrium, we need to satisfy this condition. That is moment of BA plus moment of BC should be equal to 0. That is the net moment at joint B should always remain 0, because if there remains a particular moment value on joint B, then that joint would get rotated because of that moment value. So we don't require any moment value at any joint, therefore, except the fixed joints of course. So therefore we need to keep those joint values as 0. So MBA plus MBC equal to 0. We just have to substitute the slope deflection equations of MBA and BC. This is the slope deflection equation of MBA, and this is the equation of MBC equal to 0. I simplify this, I get 2 theta b plus 0.5 theta c minus 3 delta by 16 equal to 5 by EI. So I got this equation in terms of theta b, theta c and delta. To solve this equation, I need two more equations because the unknowns are 3, right? And to solve three unknowns, we require at least three equations to get the value of theta b, theta c, and delta. So the next equation I'll get by writing the joint equilibrium condition at joint C again. So MCB plus MCD would be equal to 0. Now this is MCB, this whole equation is MCB, this whole equation is MCD, and it is equal to 0. I simplify this, I get 0.5 theta B plus 1.8944 theta C minus 0.1479 delta equal to minus 5 by EI. We name these two equations as 7 and 8. So this is the second equation, and we require one more equation now just to solve uh, them simultaneously. So third equation, now we do not have any other joint for which we can take the joint equilibrium condition. Okay, because A, B, C, D, these are the only four joints, and A and D are fixed. So we cannot consider the joint equilibrium at A and D. We can only consider the equilibrium at the intermediate joints. So the next equation comes from a shear check. Okay, now these are the reactions, horizontal reactions, right? H1 and H2. Okay, we need to find their values basically in terms of MA, MB, or in terms of moment basically. So we draw a free body diagram. The reason of drawing free body diagram I'll explain you later on. Had this been a vertical member, we need not have to draw the free body diagram separately. Okay, I'll explain you why we did not require if this was a vertical member. So we'll just uh, place these reactions here, H1 and H2. You can take any direction of this reaction. Okay, I have just taken randomly H1 and H2 going to the left side, but it has a logical explanation as well, because since this force is swaying my member to the right, it is very logical that the reaction would be formed to the left, right? So I've drawn them to the left, but you can take this right, this to the right, this to the left, or both to the right, or one right, one left, anything that you want. So we just place them here, and now we have to do the equilibrium thing of AB, CD, and BC. Okay, we need to satisfy them equilibrium. At joint A, since it's a fixed joint, along with this horizontal reaction, we will have two more reactions, that is a vertical reaction and a moment. So I'll draw a vertical reaction, again assuming their directions randomly. I have assumed it one vertical and this reaction is downwards. So it can be anything. Okay. Now since this H1 is going to the left, the reactions at B would be exactly opposite to them. So if this is left, here it will be right, H1 to the right, and since this is going upwards, this would be downwards. This is just basic summation fx equal to 0 and summation fy equal to 0 for member AB. Now for member CD, again doing the same thing, summation fx equal to 0 and summation fy equal to 0. I get H2 in the right direction and V2 upwards. Okay, now we have to just translate them from this joint here, that is translating to the next member BC, and just to maintain the joint equilibrium, we have to change their directions. Okay, so if here V1 was downwards, here V1 would be upwards. If here H1 is to the right, here it would be to the left. This is just to maintain the equilibrium of the joint. And then of course there are these external loads as well. Similarly here, if H2 is to the right, here H2 is to the left, here V2 is upwards, here V2 is downwards. That's it. Now and these are the moments, of course. That is the third reaction for every joint. Okay. MAB, MBA, MBC, MCB, MCD, MDC. I have assumed all to be clockwise. Okay, that is just my assumption, because we do not yet know that what is the value of MAB or MBA, if whether it is positive or negative. If it is positive, then clockwise is correct. If this comes negative, then it means that the direction is anti-clockwise basically. But right now, since we do not know their values, we can assume them all to be clockwise, because we can assume them to be positive, right? So once we have just drawn all these moments here, now what we will do is take the equilibrium of column AB. summation MB equal to 0. So I'll write the summation MB equal to 0. That is H1 into 4 plus MAB plus MBA equal to 0. I directly get the value of H1 in terms of MAB and MBA. But again, this equation will not give me the third equation that I require. Basically, we are doing all these things to find that third equation, which will fetch me my value of theta b, theta c, and delta. Okay, because till now we have only two equations with us. We need the third equation. Now, equilibrium of column CD, again doing summation of MC equal to 0. Minus H2 into 4 minus V2 into 2 minus MCD minus MDC equal to 0. Basically, I am getting this negative because my sign convention of writing bending moment is of sagging and hogging concept. That is, if I need to find the value of MC, I'll fix this point and I'll check what this force is doing to my member. So this force is basically trying to bend it this way, which is causing a hogging shape or a sad shape, which is basically negative. Again, B2 is trying to hog my beam, therefore it's negative. So all these basically are negative for me, but you can assume any sign convention of bending moment, how whatever you follow, and whichever is easier for you. Now, when we solve this equation, we actually cannot solve this equation any further because we do not have the value of V2 as well as we do not have the value of H2, and that is the reason we need to draw this free body diagram just to find the value of V2. Okay, V2 and H2. Had this been a vertical member, as you see here, H1 we directly got it in terms of MAB and MBA. Had this been a vertical member, we would have got H2 in terms of MCD and MDC. So it would have been very easy. You did not have to draw the whole free body diagram for it. But just to find this vertical component, we need to find the free body. We need to draw the free body diagram. So now we'll find this vertical component somehow. So let's see what we can do now. So column AB and column CD are done. Next would be beam BC. Summation MC equal to 0 again. So V1 into 4 plus MBC minus 10 into 2 plus MCV equal to 0. We get V1 in terms of the moments. So we found V1 but yet not V2. But we can somehow deduce the relation between V1 and V2. We'll see it next. Okay. Now this is equilibrium condition of the entire structure. Right. First doing summation Fi equal to 0. So plus V1 minus V2 minus 10, that is all the vertical things, plus V1 minus V2 minus 10 equal to 0. I got V2 in terms of V1, right? V2 equal to V1 minus 10, and V1 I already have in terms of the moments. So V2 also I can write in terms of moments, right? And this 10 is basically a constant. So I got V2. Now I need to eliminate this H2 as well because I need the whole equation in terms of moments only. Only then I can basically substitute my slope deflection equations of MCD, MDC, and all those things, and then I'll get in terms of theta b, theta c, and delta. So how to find this H2 basically? So summation fx equal to 0. I get H1 plus H2 equal to 50. Now I have this relation now, okay, that H2 equal to 50 minus H1, and H1 I already have in terms of moments. So H2 also I got in terms of moments basically. So now here in this equation, everything is in terms of moments. We just need to substitute them now and we'll do it in this step. This was basically minus H2 into 4 minus V2 into 2 minus MCD minus MDC equal to 0. We'll substitute H2 and V2. I've just basically taken negative outside and then it goes to the right hand side and it vanishes. So everything has become plus. This is H2, that is 50 plus H1. This was H1, right? And into 4, this 4 plus this is V2, whole thing is V2. This is V1 minus 10. This is V1, right? V1 minus 10. This whole thing becomes V2 into 2 plus MCD plus MDC. Now we just have to simplify this equation. Very easy, okay. So basically I have multiplied 4 inside, so it is 200 plus MAB plus MBA plus I'll multiply 2 inside now. So it is 20 minus MBC plus MCB the whole divided by 2 minus 20 plus MCD plus MDC. So basically to eliminate this denominator, now I'll have to multiply the whole thing by 2. So let's multiply. So it's 400 plus twice of MAB plus MBA plus 20 minus MBC plus MCB minus 40 plus twice of MCD plus MDC equal to 0. Okay, now we'll take all the constants to the right hand side. That's 400 plus 20 minus 40. I think we get this as plus 380, and when it goes to the right hand side it becomes minus 380, and this is in terms of the moments. Now we just have to substitute all the slope deflection equations of these moments basically, and we get a big equation. This is basically MAB MBA twice of it minus MBC. Yeah, this is MBC plus MCB plus twice of MCD and MDC equal to minus 380. Alright, and I would now basically simplify this step by step. I'll directly write the equation that I have got. You can simplify this on your own. It's very easy, nothing very much complicated. So the final equation that I get is 1.5 theta b plus 1.1833 theta c minus 3.2166 delta equal to minus 380 by EI. And this is the third and final equation to find theta b, theta c and delta. I'll name this as equation 9. Solving equation 7, 8, 9 together. First writing them down. These are 7, 8, 9 equation, and we need to solve them together to find theta b, theta c and delta. Solving them, I get theta b equal to 13.3744 by EI radians, theta c equal to 3.6455 by EI radians, and delta equal to 125.7152 by EI meters. Right. So this is what you get as theta b, theta c, delta, and if you see all are positive, that means this theta b is basically clockwise, a clockwise rotation. Theta c is also a clockwise rotation, and delta is a horizontal deflection. Okay, that means delta, the value that of what we had assumed, or the diagram, if you remember the diagram of sway, it was to the rightwards. It means that the structure is indeed going a rightwards and swaying, since we got this as positive. Alright, now we just have to substitute these values in our slope deflection equations to find the final moments. And after we substitute, we get MAB as minus 40.456, MBA minus 33.7688, MCB plus 33.7688, MCB 38.9043, MCD minus 38.9043, and MDC minus 40.5346. So this is a anti-clockwise moment, anti-clockwise, clockwise, clockwise, anti-clockwise, and anti-clockwise. We got all these values by substituting theta b, theta c, and delta in slope deflection equation. And the last step that remains is basically to draw the bending moment diagram, which is quite self-explanatory. Okay, bending moment diagram is nothing difficult to draw, and this basically completes our problem of slope deflection method for the frame, this portal frame with an inclined leg. And you can compare these values with our moment distribution method. I'll be posting the link here in the show notes or in the description as well. You can compare these two methods and how to solve them. I hope this lecture was informative to you, and if you liked it, then please like this video, share it, and subscribe my channel for more such informative videos. Thank you so much.